life expectancy statistical approach. Thank you. So I'm going to speak about evacuation of person and how many chances we have to go out of a building when entering it. When a fire breaks out, the question is that once evacuation is unique and often is not repeatable. I mean, if the fire breaks out right now here in this room, we are going to evacuate, to go out, and there is no chance that if the fire breaks out another time with the same people in the same place, we got the same result in the evacuation. And moreover, each individual experience of this is unique and is not repeatable. And one of the points is that fire safety engineering is no forensic. We are not talking about what has happened, but what may happen. So, in that case, one fire is not all fire, and if we consider only one, we can't draw any conclusion. And moreover, once evacuation is not all kind of evacuation possible. So, because there is an almost infinite set of exposure scenario, I mean, when I evacuate from this place under fire, I'm exposed to smoke and heat and so on. And so, this unique experience, there are almost an infinite possibilities of this. So, to take into account all this and to know if a building is safe or not, and to get a mark to that building or to a transportation place, for example, then we have to take a statistical approach because comparing them to buildings or to evacuation strategies is not that simple. So first, a word about the effect of fire on people. Usually, according to ISO 13571, we have some effects that are listed: irritating gases, narcotic gases, thermal and visibility. And the most important point about that is that some of the effects of fire are instantaneous. It means that, for example, irritant gases, when you breathe those irritant gases, you are instantaneously impacted by it. When talking about narcotic gases, you breathe the gas and then you are impacted all the way you breathe that gas. It means you accumulate dose of the gas and you may be incapacitated after a while. So here is an example of the, this is not a red one. Yes, there is an example and we see that the most important factor is the time here in this kind of formula because it's an explanation of those. So some words about widely used concept, A set and R set. And when I went to this point, I wasn't sure at all of what was A set and R set. I had some notions, but I was not sure myself. So I went back to the reference document. So ISO 16738, and this is about evacuation, and this one is about vocabulary. And even in those documents, reference documents, you have some slight differences. And moreover, when you think about ASET, the available time you have when you are escaping, this cannot be seen as a unique scalar value. Just because, say, if fire takes here and we have to go that way, or if it takes there and we have difficulties to go out that way, this is not the same. And a global A set for one entire building is something not very pertinent. You have to consider local places. And of course, A set also depends on the way you take and the kind of gases you accumulate when breathing in this evacuation. I mean, imagine you and I were going out and we are coming at the door and there is smoke in this place. If I go out first, I get lucky and a little bit rude because you are a woman and you should go first. If I go first and you stay a little bit, then you accumulate more gas And when we are out of this, if we consider we encounter exactly the same conditions in the corridor, I have more time ahead than you, just because my FED, my dose of narcotic gas is less than yours. So ASET is also person dependent and depends on what decision has been taken and so on. So ASET is time, space, and person dependent. The problem is the same with RSET, of course, because effects from fire affect the traveling speed. It also affects the judgment. I mean, if I have breathed enough narcotic gas, I'm not sure I will be quite able to take pertinent decisions about the way I have to take. Should I go left or right or whatever? So, RSET is also time, space, and person dependent. So there is a requirement for a finer grain analysis that just comparing a global ASET to a global ASET. So in 2008, we have begun a work in France which was called GTTOX, and we went to a methodology which was a risk analysis oriented methodology, modular and versatile, which was designed to take more gas than was the rule in France at that time. Kinetic of basis production, ventilation condition, and regime of combustion, and so on. And also all the effects that can be encountered from fire on people, thermal effect, toxic effect, effect on visibility, and of course walking speed and so on, and evacuation chance. So this methodology has been adapted right now in 2011, and it is presented here in a statistical approach. So the first work is a risk analysis. The risk analysis tells us what scenarios are interesting scenarios to be studied in further analysis, in deeper analysis. The output from this risk analysis is room of interest with fire scenario. And of course, you must have probabilities, estimated probabilities, and this is one of the difficulties of this work, to estimate how often a fire may occur. For example, if you rely on feedback, experience feedback, then you may have a big bias because some very rare events are not really experienced. So how can you estimate the probability of this? Then when you consider all possible scenarios, you have to build the fire design curve related to that scenario. And the scheme we have employed is a scheme with a matrical scheme which allows us to list for each combustion regime you can find here, and for each gas that you want to consider. And because it is modular, you can add as much as column as you want and as much as gas as you want. And we here have the pattern of production of species related to that fire. And of course, this is of a room, so it includes the participation of all the material in the room, and we have to estimate what kind of gas each material will be able to produce. Of course, there are some simplifications. We do not deal with the interaction between two materials burning together, but at some point it goes further than what we had until now. And of course, we have to estimate the heat release rate curve. Then, when we have that point, we have to know where are the danger, the hazard in the building, and at what time. So have a cartography of the species and the temperature, radiation, and so on at each time step. So to do that, we use CFD calculation, and because we have several combustion regimes, and because we don't want to rely on any given combustion model, we use